Assalamualaikum and a very good day everyone. Welcome to Hydraulics and Hydraulic class for chapter 4 Rapidly Varied Flow or Hydraulic Jump in Open Channel. The outline of this topic is Introduction, Hydraulic Jump, Type of Jump, Momentum Principles, and Practical Application. The hydraulic jump is under CO number 1, CO1, which is to analyze the non-uniform flow in open channel. And by the end of this chapter, students should be able to determine and calculate conjugate depths, energy dissipated, and power dissipated in open channel. Hydraulic jump analysis is the common application of the momentum equation in open channel. Hydraulic jump is an abrupt change in depth from supercritical to subcritical flow, always is accompanied by a significant energy loss. Hydraulic jump primarily serves as an energy dissipator to dissipate the excess energy of flowing water downstream of hydraulic structures such as spillway and sluice gate. As we mentioned earlier in chapter 1, the type of flow can be classified according to time, space, viscosity, density, and gravity. The rapidly varied flow is under the classification of non-uniform flow. It can be seen here that the rapidly varied flow is under the classification according to space, where a flow can be classified as uniform flow and non-uniform flow, where the rapidly varied flow is one type of non-uniform flow. The non-uniform flow is when the flow depth varies with distance. Let's say, for example, at the length of 1 meter, the flow depth is 1 meter. But when the length changed to 2 meters, the flow depth also changed to 2 meters. It defines the rapidly varied flow where hydraulic jumps occur when the flow depth changes rapidly over a relatively short distance from a supercritical flow to a subcritical flow. Okay, let's look at this figure. When this figure it shows that there are GVF, which is gradually varied flow, and RVF, which is rapidly varied flow. The gradually varied flow is where the flow changes rather slow with distance, and the water depth is lower. And the hydraulic jump is occur here when the water depth changes speedily at rapidly varied flow. The hydraulic jump is often used downstream of spillways and drop structures to dissipate energy and prevent erosion in the downstream channel. The hydraulic jump occurs from supercritical flow to subcritical flow. The supercritical flow can be classified when the Froude number is more than 1, while for subcritical flow, the Froude number is less than 1. So how are we going to determine the Froude number? The Froude number can be determined using this equation where V is divided with square root of Gy, where G is the gravitational force and Y is the water depth. Okay, as been mentioned earlier, the hydraulic jump is the transition from supercritical flow to subcritical flow. And this figure shows that a transition between subcritical flow here become the supercritical flow and then becomes subcritical flow again and cause the hydraulic jump to occur. The instant turbulence in the jump causes mixing and energy dissipator. One application of hydraulic jump can be seen here using sluice gate, where the hydraulic jump occurs here from the transition between supercritical flow to subcritical flow. And this is application in laboratory using the open channel device. Well, this is the real-life application of hydraulic jump in the spillways. There are a few types of hydraulic jump depending on the Froude number. If the Froude number less than 1, no jump occurs since the flow is already in subcritical. While if the Froude number is equal to 1, the flow is critical, hence no jump can be formed. In the range of Froude number 1 to 1.7, the water surface shows undulations and the jump is called undular jump. If the Froude number between 1.7 to 2.5, the jump may be called weak jump, while oscillating jump occur at Froude number between 2.5 to 4.5. And for Froude number between 4.5 to 9, the jump is called steady jump, where the energy dissipation range from 45 to 75%. For Froude number 9 and or larger, it is called the strong jump, and the action is rough but effective since the energy dissipation may reach as high as 85%. The analysis of hydraulic jump involves a few equations which related to the momentum principles. In hydraulic jump analysis, we can determine the height of hydraulic jump, which is yg, the conjugate depth y1 or y2, and also energy dissipated and power dissipated. This is the assumptions in the relationship between hydraulic jump and momentum equation. There are several assumptions here, where the channel bed must be flat, the channel cross-section uniform, and the velocity and water depth also uniform. Ignore the stress at channel surface, it must be frictionless, and hydraulic jump occur at short distance. And from this Newton's second law, the change of momentum per time equal to combination of external force. And we have mass in equal to mass out. This is the sample observation for conjugate depth equation, which is all the lead for this, the derivation for all these hydraulic jump equation. We have the equation for hydraulic jump height and depth, conjugate depth, energy loss, and power dissipated. This is the practical application of hydraulic jump, which is to dissipate energy in water flowing over dams, weir and other hydraulic structures, and thus prevent scouring downstream from the structures. And to recover heat or raise the water levels on the downstream side of a measuring flume, thus maintain high water level in the channel for irrigation or other water irrigation or other water distribution purpose. To increase the weight on an apron and to reduce uplift pressure under a masonry structure by raising the water depth on the apron, and also to increase the discharge of the sluice by holding back tailwater, since the effective heat will be reduced if the tailwater is allowed to draw the jump. Hydraulic jump also used to indicate special flow conditions such as the existence of supercritical flow or the presence of a control section so that a gauging station may be located. And to mix chemicals used for water purification and to aerate water for city water supply. Okay, let's look at example 4.1. At the bottom of a spillway, a rectangular channel with 30-meter width, the velocity of flow 28.2 meter per second and the depth before jump is 0.96 meters. The hydraulic jump is immediately occur. Calculate the height of hydraulic jump and the power dissipate. Okay, let's see the solution for example 4.1. First of all, we have to outline all the given data. Okay, so B, width of channel, we have 30 meters, velocity 28.2 meter per second, and Y1 0.96 meters, and you have to find Yj, the depth of the hydraulic jump, and P, power dissipate. So this is the sketch for this problem where we have the Y1, the depth before the hydraulic jump is 0.96 and the depth after the hydraulic jump is Y2. This is the height of hydraulic jump, and the velocity at point 1 is given as 28.2 meter per second. Okay, first, to find the depth of hydraulic jump, we can use equation 4.1, Yj equal to Y2 minus Y1, where the Y1 is 0.96 meters given in the problem. And the problem is we need to find the Y2. So Y2 can be obtained using equation 4.3, the equation for the hydraulic conjugate depth. We have Y1, but we don't have the Froude number, Fr. But the Froude number can be obtained using formula V divided with the square root of Gy. So V has been given in the problem 28.2 and Y1 is 0.96. So substitute this value into the equation, you will obtain the Froude number 9.189. And then with the substitute the value of the Froude number into equation 4.3, the Y2 will give you 12.005 meters. You can see here that the Froude number at point 1 is 9.189, which is more than 1. So when Froude number more than 1, so the types of flow here is supercritical. Okay, so substitute the value of Y2 into equation 4.1. You will have your depth of hydraulic jump is 11.045 meters. So now we find the power dissipate. you can use equation 4.6, which is P equal to rho G rho G Q delta E, where the Q can be obtained from general equation of flow, Q equal to VA, and because this is a rectangular channel, so the A equal to B times with Y1. And then for delta E, can obtain from this equation and substitute all the value that we have. Y1 equal to 0.96, B 30 meters, you will get the Q 812.16 cubic meter per second, and delta E 29.228 meters. Hence, substitute the Q and delta E into equation 4.6. You will have P equal to 232.867 megawatt. So please redo this example in details and compare your answer with the final answer given. Okay, let's look at the next example, which is example 4.2. In a rectangular channel with 0.6 meter width, hydraulic jump occurs when Froude number is 3. Normal depth before the jump is 0.6 meters. The question asks you to determine the energy loss, delta E, and power dissipate, P, in this situation. First, outline all the given data in the problem where we have Froude number 3, Y1, the depth before the jump is 0.6 meters, and you have to find delta E and P. Delta E can be obtained from equation 4.5, and however we don't have the value of Y2, so Y2 can be obtained using equation 4.3, the conjugate depth equation. The Froude number is already given in this example, which is 3, so just substitute the value of Froude number 3 and Y1 0.6. You will have your Y2 equal to 2.263 meters. Substitute the value of Y2 and Y1 into equation 4.5. You will have delta E equal to 0.848 meters. Okay, for P, power, you can use equation 4.6. And how to find the Q? Q equal to AV, and for rectangular channel, we find A by B times Y1. And however, we don't have the value of velocity. The velocity can be found by applying the formula of Froude number. As we already have the Froude number 3 and Y1 0.6, substitute into the equation, then we will have V equal to 7.28 meter per second. And then the Q is 2.62 cubic meter per second. Substitute all the value V and Q into equation 4.6. You will have the power equal to 21.795 kilowatt. Okay, let's look at the last example, example 4.3, where hydraulic jump occur in 0.5 meter width rectangular channel at the point where the depth of water flow before the jump is 0.15 meters and the Froude number is 2.5. So you have to find the specific energy, critical depth, conjugate depth, loss of heat, and the power dissipate. The data given, Froude number 2.5, y1, the depth before the jump is 0.15 meters, and the width of the channel is 0.5 meters. Okay, first you have to find the specific energy E1. The equation for specific energy E can be obtained in the previous chapter 3 in equation 3.5, where y1 plus q1 squared over 2g y1 squared. You can see here that we use the small q. The small q here can be obtained from equation flow divided with the width of channel. However, we don't have the flow value. So the flow value can be obtained using the general flow equation Q equal to AV, where we have the value of B 0.5 meters and Y1 equal to 0.5 meters. You need to find V, velocity. So we can apply the Froude number equation. We have Froude number equal to 2.5 and y1 is 0.15 meters. So V is calculated as 3.033 meter per second. So you substitute the value of V here into this equation, you will obtain the Q value equal to 0.227 cubic meter per second. Then the Q value will be substituted into this equation, and we will have our small q value is 0.227 cubic meter per second divided with the width of the channel 0.5 meters, and we have 0.455 cubic meter per second per meter. Substitute the value of Q into equation 3.5, then we have the specific energy as 0.619 meters. Okay, next you need to find the critical depth, YC. The critical depth also can be found from equation from previous chapter, which is chapter 3, which is YC equal to square root power of 3 of Q power of 2 divided with G. And then we use the Q from the previous calculation, and G, the gravitational force, with 9.81 meter per second power of 2, we will get the YC equal to 0.276 meters. Conjugate depth Y2 has been solved earlier. You can find the Y2 from equation 4.3, which is Y2 over Y1 equal to 1 over 2 times with square root of 1 plus 8 Froude number power of 2 minus 1. In this question, the Froude number is already given 2.2 and the Y1 is 0.15, and then we obtain the Y2 equal to 0.461 meters. Okay, to find the head loss, we use equation 4.5 with we already have the Y1 from the problem 0.15 and Y2 0.461 from the previous calculation. So the head loss of head equal to 0.108 meters. Okay, the last one, you have to find the power dissipate P, and from equation 4.6 we have Q from the previous calculation 0.227 and delta E 0.108. Then you substitute this data into the equation 4.6. Then we have the P equal to 241 megawatt. Okay. Okay, by referring to the three examples given before, you may try to do this exercise 1 and then compare your answer with the given answer, and exercise 2, also exercise 3. Okay, thank you class for listening. Thank you.